Great pleasure to welcome Davide Bigoni, who is a really famous professor of mechanical engineering working at the University of Trento in Italy. So please, Professor Bigoni.
Thank you. I will do my best because I'm not very used to Cisco WebEx. And so first thing I have to do is to share the screen. Yeah, I'm not mistaken. And by the way, these kinds of presentations done in the internet for Italians are bad because, you know, Italians need to hand waving. So I'm sorry for people who will not see my hands going around. So ladies and gentlemen, thank you for this opportunity. I'm happy to give this talk. Hope that you will enjoy. Speaking of metamaterials, shear bands, and invisibility. First of all, I would like to introduce my research team, and now I'm going to find how to. Sorry, I'm working with this. Okay. 1 second. I need 1 second to pick up. Then. Yes. So my co-workers are Giovanni Bodiga, who is postdoc in my department, Luigi Cabras, who was postdoc at my department, who is now postdoc at the University of Brescia, and Andrea Picoros, who is associate professor in my group. So I would like to start speaking about shear bands. So we see here on the left an impact sample of clay, and on the right here we see the same sample after a compression test. What we may see is that the deformation is not uniform, but is highly localized into a band. We see this band here. And inside this band, there is an intense shearing occurring. So this is an example of localization of deformation. Better to speak of localized shear bands because the material inside the band suffers huge shearing deformation. According to the definition of Jim Rice, who gave this definition almost 40 years ago, shear bands of strain localization form when an essentially smooth and continuously varying deformation pattern gives rise to a highly localized deformation. Well, from the mathematical point of view, shear bands and strain localization occur at the elasticity loss of the differential equation governing the incremental deformation of a solid, while the elasticity loss corresponds to the singularity of the acoustic tensor, which governs the propagation of acoustic waves into a material. Now, often shear bands persist, and these are examples of shear bands that I have encountered in my life. We see the sample of before, and we see here another example of a sample where the shear bands have an X shape. So there are two inclined shear bands equally inclined with respect to the vertical direction. Another example of the same kind of localization is this, where we see this damage inclined at two shear bands. This rock, and also this other rock, which I like because this is a runestone. It's a photo of a sample exposed in the Museum of Edinburgh. And I like to think that all these shear bands that you may see here were considered by ancient people as signs of God. While other shear bands are here in an iron meteorite. This is a piece of plastic where we see again the same shear bands. And often what we see is the signature of shear bands, because shear bands often degenerate into a regular pattern of fractures. We see here fractures in wood, here in a tree trunk, in a painting, and so on. So what I'm telling you, what I'm proposing today is the following. Usually shear bands are accompanied by large plastic deformation and just emerge before failure. So they come together with damage and eventually fracture. Moreover, the shear bands, the mechanical features of shear bands are dictated by the material. I mean, for a certain material, there are a certain number of shear bands, a certain inclination. If we would like to change these features, that's difficult because we have to change the material. Nowadays, we are looking to architected materials. These are materials with extreme properties, for instance, foldability, channeled response, surface effects, and we would like to have the possibility of switching shear bands on and off without any damage. Because in this way, we will pave the way to the use of a material that can be designed to produce these kinds of instabilities. And our idea is to be able to exploit these instabilities for practical purposes. Well, in this sense, shear bands have to occur well inside the elastic range and far from failure. Otherwise, we will not have the possibility of switching them off and on. Shear bands should be designed to have desired features, inclination, number, and we would like to have a system to induce or inhibit the appearance of shear bands. All the mechanical parameters in our artificial materials, we would like to be rigorously determined, possibly analytically. So how to solve this problem? Well, I'm proposing you to use a specific kind of artificial materials that we see sketched in this figure. So the idea is to use periodic two-dimensional grids of axial and flexurally deformable elastic rods. And these elastic rods have to be axially preloaded in tension, as you see in the sketch, or in compression, and subject to in-plane incremental deformation. I'm highlighting this concept of in-plane because in the literature there are a bunch of results for structures loaded out of plane. But in this case, we are working in the plane. And so we should think that every elastic rod is subjected to bending moment, to shear force, and axial force. So the idea is to take a grid and to subject it to tensile or compressive axial force, and then perturb it with a deformation inside the plane. What we have to do to treat this problem is to consider the equations governing axial wave propagation and transverse wave propagation for time harmonic assumption. So we see that we have to deal with the mass density, the linear mass density of the rod. We have the axial displacement, the circular frequency, the axial stiffness of the rod, which is usually written as EA. And now what we see is that these parameters depends upon the pre-stretch that we impose before the incremental deformation. So the first equation is for axial deformations. The second equation here is for transverse vibrations. And so V is the transverse displacement. Omega is always the frequency, the circular frequency. Gamma, the linear mass density. B is the bending stiffness, often is written as EI. P is the effect of the preload here. And eventually, we see that we have also introduced the so-called rotational inertia, which means that our beam model is a Rayleigh beam model. Of course, the Euler-Bernoulli model is recovered when gamma R is set equal to 0. For these differential equations in the time harmonic regimes, the solution exists and can be written in this form, where we have all these parameters defined in this way, and eventually all these equations boil down into a matrix representation like this, where we have the generalized displacements on the left, and on the right, the generalized displacements at the ends of the rod. And this matrix N collects the Prestress-dependent shape function. Don't be confused about the name shape functions, because these shape functions are rigorously determined analytically. So there is no approximation here. Well, with this equation, we have to collect the energies for the prestressed grid of rods. And so we have the kinetic energy, which is written in the usual way as 1/2 the mass times the velocity squared. The elastic energy is the sum of the axial elastic energy and the bending energy. And finally, the potential energy contains the effect of the pre-stress P loading the elastic rods. So all these equations end up in a Prestress-dependent stiffness matrix. There is nothing particularly new here. This stiffness matrix is known and has been determined analytically. And now we are in a position that we have to select what to do. So we can follow two ways. One way is to use homogenization, and I will speak of this in a few minutes. The other way is to directly use these equations for the grid, introducing a Floquet-Bloch technique. So for doing this, we have to consider compatibility of displacement and rotation at the central node of the unit cell. Then we have to impose the equilibrium of this node and the so-called Bloch-Floquet boundary conditions that we may see listed here, where these key 1 and key 2 are the in-plane components of the Bloch wave vector. If we do this for the grid of the beams, we arrive to a dispersion equation, which depends on the aspect ratio between the length of the rods, the ratio between the cross-sectional areas of the rods, and the slenderness of the rods. And eventually, through a renormalization, we arrive to a final expression for the dispersion equation, which is this one. And this equation can be solved numerically up to a desired precision, because the solution of this equation is not a real problem. And in this way, we obtain results in terms of dispersion surfaces. So these surfaces are very popular nowadays, but to tell you the truth, they leave me a little bit cold, because it is something that is not particularly interesting to see. For instance, on the left, we see the dispersion surface obtained in the limit of the Euler-Bernoulli behavior. In the center, when the Rayleigh beam enters into play, and we may see that the difference between these two is only evident at high frequency, and this is expected because rotational inertia only plays a role at high frequency. And on the very right, we see another example where we have played with the slenderness of the elastic rods. So I don't have much to say about these surfaces, except that we can try to hunt for spatial features. And we may see here a couple of these spatial features. For instance, on the left, we see here a flat band. This means that we have an infinite set of standing waves propagating all at the same frequency, which is exactly 1.971. And this occurs at a slenderness ratio equal to 6.192, exactly at that slenderness and exactly at that frequency. Or if we look to the right, we see other things that we can do with this dispersion surfaces. We can look for Dirac cones. There is one here, another is there. There are many more, so another is here. But this is not another there. This is not the thing I would like to speak about. I would like to concentrate on the second possibility. The second possibility is to introduce the homogenization of the lattice to get an equivalent solid, because our goal is to obtain materials which behave in a particular way, which is determined before doing calculations, possibly analytical calculations. So we would like the two-dimensional grid to behave as a material. And so this is the homogenization problem. We start from a stress-free configuration. The stress-free configuration is pre-stressed, say, in tension, but it can be pre-stressed also in compression, to get a grid which is larger than the initial configuration. And the current configuration is perturbed through an incremental macro deformation, which introduces bending, shear forces, and axial incremental deformation. So the lattice is two-dimensional, periodic, and subject to in-plane incremental deformation. So if we want to continue with the way of homogenization, we have to introduce a unit cell. So this unit cell is generic, and in fact, we have developed a tool which allows us to treat completely generic cells, and we have to impose the conditions coming from the spatial periodicity. In dynamics, they are called the Bloch theorem, which is this. In statics, they are called the Cauchy-Born hypothesis. It is a way to enforce spatial periodicity of the system. So this is from the point of view of the lattice. Now let's have a look to the point of view of the continuum. We have to compare with the continuum, which is initially stretched homogeneously and then is subject to the incremental deformation. So the incremental strain energy can be found in every block, is made of a first order component, which is the Cauchy stress scalar, the gradient of incremental deformation, plus a terms of second order where we see the elasticity tensor coming into play. See, the elasticity tensor can be defined in this way, and it rules the relation between the the gradient of incremental displacement and the increment of the first Viola-Kirchhoff stress tensor. So the form of the comparison material of the equivalent continuum is standard. And what we do have to impose the homogenization scheme is to match in statics the first order energy in the continuum with the first order energy in the lattice. And similarly, we have to enforce matching between the second order energy in the continuum and the second order energy in the lattice. This is what we have to do. In statics, things are not particularly complicated, but they become more complicated in dynamics, where we have to match on asymptotics, and we have this as a solution of a sequence of linear systems. So things here are more complicated, but they are not new, because there is a well-established framework in the literature which was developed mainly by Nick Triantafilidis, Pedro Ponte Castañeda, and John Willis. So this technique of dealing with problems of dynamics does not require invention of new things, but it requires to refer to an established framework. So before to show the results of the homogenization of the lattice, I would like to speak about the role of homogenization. So I would like to put a question on the table: when homogenization does work and when does not. So I would like to start with a few examples of experiments that I have found in the literature. So more or less here, these two papers. We see on the left and on the right here examples of grids of elastic rods which have been deformed in compression. And in these two cases, the first instability encountered in the loading path has been a so-called macro bifurcation. So a bifurcation in the lattice, which is detected with the Bloch-Floquet technique, and it exactly corresponds to a loss of ellipticity in the equivalent material. We see it here. This is the analytical computation of this situation, and we see a form of global bifurcation. When the grid has a global bifurcation, it has been proven by Triantafilidis and Ponte Castañeda that this instability corresponds to loss of ellipticity, and as I said, it corresponds to shear bands or localization of deformation. This is the case where homogenization works. This other case is an experiment that I did in my lab, and it is a compression, a confinement compression of a stack of drinking straws, which are arranged initially in a hexagonal geometry. And then when we squeeze the sample, we see almost immediately the formation of an ovalization. and we see that the ovalization quickly spreads throughout the sample. After this ovalization, we eventually see the localization of the formation into bands, and we see also that this localization progressively accumulates. But the first instability is this kind of ovalization. And well, if we analyze this instability from the theoretical point of view, we came to the conclusion that this is an example of micro bifurcation. So it's a bifurcation occurring in the lattice, but it's not an instability for the equivalent continuum. So the equivalent continuum does not see this kind of instability. And so it does not work as a material able to capture this instability. And so this is the situation. We have two possibilities when we load a grid of axially preloaded elastic rods. The first possibility is the early occurrence of a microscopic bifurcation. In this case, the homogenization scheme does not work because this microscopic bifurcation remains undetected in the equivalent material. So from this point of view, the equivalent material is somehow useless. In other cases, we see something different, a macroscopic bifurcation like this one, and this is detected both in the grid, in the structure, and in the equivalent continuum. And in the equivalent continuum, it corresponds to a loss of ellipticity of the equations, which means a possibility of a localized deformation in terms of shear band or dilational band. These results are not our results, but have been demonstrated mainly by Nick, Trento and Ponte Castagnolo. And now I would like to show you an example. We have selected this grid of inclined rods. The rods are inclined at angle alpha and have been reinforced through these linear springs, which only provide a transverse reinforcement to this grid. And so with this structure, we are able to apply the homogenization tool, and we are able to define the equivalent material. So first thing we have to do is to obtain the prestressed tensor in the equivalent solid. And we see that the formula is pretty nice. It's this one. We see on the left the Cauchy stress in the equivalent material. Alpha is the inclination of the grid. L is the length of the rods. And P1 and P2 are the two components of prestress in the elastic rods. This is a first order. But now, of course, we have to go at the second order, which is the most important part. And things here become a little bit more complicated. We have 10 components for the elasticity tensor C, and they are listed here. Don't be afraid about this formula because they are all analytical and they can be treated easily using a symbolic manipulator. So we can write down and use this equation to design our material. So our goal is this equation define an artificial material that can be designed by us because we can change the inclination of the rods alpha. Sorry, alpha is here. We can change ratio governing the stiffness, the slenderness of the rods, and so on. And now these are results. So on the left, we see this graph where there are P2 and P1 in the axis, which are the two components of the prestress of the elastic rods. Well, when only the horizontal prestress is present, like in this case, we follow a horizontal path in this graph, like this one. When both components are equal, like in this case, we follow a path which is inclined at 45 degrees. When we are inside this domain, which is sketched purple, the solution is unique and stable. When we hit this boundary, something simultaneously occurs. We have the simultaneous occurrence of a macro bifurcation in the lattice and in the solid. So both the lattice and the equivalent solid we have in the same way. And so here we are in the business of the homogenization. In this other case, what is the difference between these two cases? Well, the diagonal springs here are 0, and here we do have these springs. So now with these springs, we see that the things are more complicated because the two domains for macro and micro bifurcations are not superimposed. So it happens that if we load horizontally like this, then we simultaneously hit both boundaries. And so for this loading path, the homogenization technique does work, and the first instability is a localization of deformation. But if instead of going in the horizontal direction, we go in the inclined direction, we see that we hit before the boundary of micro bifurcation. And so the equivalent solid is completely indifferent to this kind of instability. It's completely undetected. So in this case, the homogenization scheme is not really useful to our purposes. Well, we have introduced these conditions, and now I would like to show you something, because maybe you might think we have spoken of macro bifurcation, but why a macro bifurcation should correspond to a localization of deformation to a shear band? Maybe this is not yet clear. And to make this clear, we have to reveal the existence, the possibility of localized deformation. How to do? We use a strategy which we developed years ago together with Professor Willis. And the idea is the following. Our material is taken to be infinite. It's an infinite material, like the Bezier sketched here. And we perturb this material by applying concentrated forces. These concentrated forces can be quasi-static or can be dynamics, but they play a role of a perturbation. So we consider this body to be prestressed at a certain value, and then we perturb it to see what happens. The perturbation is actually the solution to a concentrated force, so it's a green function. And this green function can be given an explicit form in this way. This formula was obtained some 10 years ago or so. And we can use this formula analytically to see how the material behaves near the border of ellipticity loss, the comparison material and the grid. And here we have the results. So we see the behavior of the material at increasing level of pre-stress. Initially the pre-stress is 0, and then it increases up to the vicinity of the border of ellipticity loss. So ellipticity loss corresponds to 1 here. And now the first row, this one, is referred to the grid, to the lattice material. And here, these results have been obtained through numerical simulations with finite elements. So it is the behavior of the structure. On the lower row here, it's an analytical solution because it's the green function obtained by us used for the solid obtained through homogenization. And in this case, the solid and the lattice should correspond. And in fact, they do, because if we compare the sketches on the upper row and on the lower row, we see that the maps are almost coincident. And eventually we see on the right the shear bands appearing, very localized deformation, and we see them in the grid and also in the equivalent material. So we are now in a position to say that we can envisage the possibility of designing architected materials showing shear bands within the elastic range, and these shear bands can be activated or inhibited using the pre-stress. So this is possible through homogenization. Now I would like to present a case where homogenization does not work, but in any case it's an important case. For this grid shown on the upper row, the homogenization doesn't give the same results of the lattice. So on the upper road, we have finite element solutions. On the lower road, we see the green function used for the homogenized material. We have perturbed the material with a quadrupole, so 4 concentrated forces. And in the lower row, where we have the homogenized material, we don't see much. But in the upper row, we see that the material is pretty unstable. So the grid is unstable. And this instability spreads through the whole lattice. We may see this more clearly here. These are results obtained with finite element. We are applying a dipole into the grid. And this is what happens when we are exactly at the load for micro bifurcation. So if we are exactly at that load, we don't see much. But if we move just beyond P1.05, the critical load, or P1.1, the critical load, then we see that there is a sort of explosion of the material. The micro bifurcation, which is undetected in the homogenized material, spreads throughout the whole body. So I would like to continue presenting results on the dynamics of shear bands. So I can say that after 40 years of research in shear bands, many problems are still unsolved. One of these problems is, how do shear bands behave under dynamic excitation? And now we are in a position to try, because we have an homogenization scheme working for dynamics, and we have also a perturbation, a green function working for dynamics. And so this is our goal, is to look to homogenization in dynamics using Floquet-Bloch wave asymptotics. In this case, instead of the elasticity tensor, the tool brings us immediately to the acoustic tensor, and then directed to the acoustic tensor. Then we have to derive the elasticity tensor, if we need it, taking this derivative with respect to the propagation of waves of the acoustic tensor. Now, how things work here? This is a result obtained for one of the cases where macro bifurcations dominate. So the first bifurcation is the macroscopic bifurcation. And so homogenization here works well. And in fact, these graphs are slowness contours evaluated analytically. And what we see is that initially at null prestress, there is the perfect coincidence between results obtained in the lattice and results obtained in the equivalent continuum. The same thing here, where the prestress is already 0.8, the critical value. And here we see a very small discrepancy there. Can you see it? It's a red dot. The red dot is the only discrepancy between the slowness contours for the lattice and the equivalent continuum. Eventually, when we are at the shear band formation, the discrepancy between the behavior of the lattice and of the equivalent continuum becomes larger, but nevertheless, we see that the equivalent continuum captures very well the shear band formation in the material. And what we see here is the real shear band. And so in this case, everything works well, and we are in a condition to design this material and to use it. And this is the final result I'm showing you about this topic. It's, again, the comparison between the lattice, and these results on the upper row have been obtained through finite elements, and the behavior of the continuum, where these results have been obtained using the equivalent material and the green function for the equivalent material. So the lower row are all analytical results, and we see how things go at increasing prestress, up to very close to the border of ellipticity. And so we see that the grid and the equivalent material behaves almost the same, and we see that going close to the elliptic boundary, we see the formation of planar shear bands emanating from the source, highly localized into a narrow shear band. We see it in the grid, and we clearly see it in the the equivalent material. So here the message is we can use homogenization, we can design composite materials, in particular grid of elastic rods, and we can do this to obtain interesting properties. Well, now I would like to speak more about metamaterials. And in the field of metamaterial, people is hunting for unusual properties, big names, quantum mechanics, negative refraction, total refraction, platonics, and so on. So I would like to show you what we can do with this simple grid of prestressed elastic rods. So this is the idea. We have an infinite grid of elastic rods, and a layer of these rods is prestressed by a tensile force, P, uniform. So this is actually an old idea because we proposed this strategy together with Max J and Sasha Motson already more than 10 years ago. So what we can do with this simple arrangement? Why to use the prestress? Well, to use the prestress is because it's very easy to add prestress and remove it. We can tune the prestress as we desire in a very simple way. We don't need to change the grid. We have only to apply loads. So what we can obtain? Can we obtain this very strange phenomena? Well, this is an example. This is, for instance, total refraction. We see here a planar wave hitting the interface with a layer of vertically prestressed elastic rods. And we see that we obtain here a total reflection, excuse me. The wave is completely reflected. And here we see another example. We have a pulsating source in terms of a pulsating concentrated bending moment. Two waves are generated. The two waves hit this layer of prestressed beam, and they are both totally reflected. So this is an example of total reflection obtained with a simple layer of prestressed elastic rods. And this is an example of negative refraction. We see again here on the left the plane wave arriving. It hits this interface with a layer of prestressed beams, partially reflected and partially refracted with a negative refraction. And if we use the pulsating source here, we see that these waves hit the layer and then they refocus here into an image. So an image is formed. It means that the prestressed beams layer behaves like a flat lens. And we can also obtain trapping and focusing of a signal. In this case, we have trapped the wave in a S-shaped channel. And in this other way, we have many things occurring because we have one layer here, another layer of different prestress there. So the same layer here, another there. And we see again negative refraction, a lot of things happening here. Then you might say, well, can we do this even simpler? Can we use simply the slenderness of the elastic rods to obtain these effects? Well, the answer is positive. Yes, we can simply play with the slenderness and again obtain total refraction, trapping of a wave, negative refraction, and as you might see here, the flat lens effect. And now I would like to perturb you saying, why to use exotic features when we can do this with simply prestressed beams or beams with different stiffness? Well, now I would like to spend a few minutes mentioning something which is sort of digression in my talk. I'm mentioning the fact that since many years, probably 10 years, I'm playing with elastic rods and plates, and I'm playing with this structure in the fully nonlinear range. Until now, what we have seen was all confined to linear behavior. Now, I would like to spend a word to say that I am convinced that there is a big world beyond linear elasticity, and we can use many effects that we have discovered in these years to think to nonlinear elastic metamaterials. And I would like to do two very quick examples without taking too much time, just to show what can be done with the nonlinear theory of flows. So this is the first topic I will speak about, the so-called dripping of an elastic rod. And well, this is based on the fact that there is a formal analogy between the differential equation governing the equilibrium configuration of an elastic rod and the shape of a free surface of a fluid meniscus or a drop. And actually, this image, which looks like a sketch, it's actually the photograph of a real experiment when we poured some resin in this container. And when we see the shape of the meniscus of resin, it fits exactly with the shape of a nonlinear Euler elastica loaded in tension. So the idea is to exploit this analogy, and we did an experiment to show that we can induce an elastic rod to take the shape of a droplet. And now this is the experiment. On the left, we see a movie with the formation of a droplet, water droplet. On the right here, we see the dripping of an elastic rod. This rod is loaded in the center with a vertical force, and it takes exactly the shape of the droplet. We see this movie another time. So the idea is to show that the analogy of the equation can be exploited to obtain non-trivial effects. And the other thing I will briefly tell you, it's something connected with the concept of configurational forces that we pointed out in the last 6 years or so. So let's speak of this experiment. We have a lumped mass which is attached to the end of an elastic rod. The elastic rod is free of sliding without any friction inside this sliding sleeve. So imagine the elastic rod is rigid or is very stiff. When we release this mass, which is subject to gravity, simply what happens is sketched here. Simply the mass goes down and the elastic rod slips inside the sliding sleeve, nothing more. But things become much more intriguing when the deformation of the rod comes into play. So imagine this is the rod and we release this mass. What will happen is that the rod will start oscillating. There will be vibration, nonlinear vibration. And this vibration, we have proven, they will generate a configurational force which is proportional to the square of the bending moment here. And this configurational force will tend to eject the elastic rod like this. So the configurational force will work opposite to the gravity. The gravity will try to make the elastic rod to slip inside the sliding sleeve, but the configurational force will try to eject it. So I will show you immediately in one experiment where we will see the mass released and the elastic rod slipping inside and then outside the sliding sleeve as the consequence of the effect of the configurational force. This is the experiment. There is a mass tracking, so we see the path done by the mass. Now we see the configurational force is ejecting the mass. Now is inserting, now is ejecting again, going out, going in, now is stopping. Here, the configurational force is balancing exactly the gravity, and now slowly goes inside the sliding sleeve. So it behaves like more or less like a nonlinear oscillation. So slips inside initially, then goes outside because the configurational force is very high, then it slips inside, and then outside again, inside, stays there because the configurational force balances the gravity, and now eventually inside. So I'm convinced that all these nonlinear effects can be exploited in the field of metamaterials. But let me now conclude my talk speaking of the last of the topics for the day, and I would like to come back to metamaterials. I introduce you a new research team, Diego Miseroni, who is associate professor in my group, and Professor Sasha Movsen, who is the pusher of this metamaterials in my life. He has introduced me to this research. And I would like to speak quickly of the invisibility and cloaking for flexural vibration. So what is the point here? What is invisibility? Imagine that a vibrating plate contains an inclusion. In our case, it's a void. Well, this inclusion usually perturbs the ambient vibration. We are looking to the condition where a proper cloaking of the inclusion makes the inclusion invisible in the sense that the inclusion does not disturb given ambient vibrational field. Actually, this is an old story in statics, because in statics it was called neutrality, and it's a research which probably goes back 50 years or so. People in statics, in elasticity, were struggling to make inclusion neutral. And we may see here an example taken from a work which was done many years ago together with Walt Drugan and Katia Bertoldi at the University of Trento. They were both at the University of Trento, Katia as a PhD student and Walt as a visiting professor. And so there is here a void which has been reinforced with these inclined fibers. And so on the left, the void is not neutral at all, it's not invisible, because we see that the stress is highly perturbed by this inclusion. On the right, we see that neutrality has been achieved, because we see that the matrix is all white, which means no stresses. And the only perturbation is confined very close to the surface of the inclusion. Well, this is in static, but I would like to speak about dynamics. So, of course, dynamic changes all this situation. First of all, I would like to mention what I have called the 7 golden rules of cloaking. There are the 7 things. I will speak you of the 7 requirements for cloaking. So, in my personal point of view, cloaking should be based on simple technology. So, my goal is try to avoid so-called exotic material, ocerat, or even worse, anisotropic density, gyroscopic, and so on. Then the cloaking, in my view, should be thin, because, of course, a very thick cloaking introduces a lot of problems. The same thing works for assuming that the cloaking should satisfy a small ratio between the dimension of the hosting medium and of the cloaked object. What do I mean with this? Imagine we have a skyscraper, and imagine I go to close to a column of this skyscraper. I take a drill and I drill a little hole in a column. Do you think that the skyscraper will be affected by this? So, of course, if the hosting medium is huge and the inclusion is very, very small, it is expected that disturbance will not affect much. And so a cloaking which works properly should work for a small ratio between the dimension of the hosting medium and the cloaked object. Of course, cloaking should provide scattering suppression. Broadband, it should work in a broadband, and should verify omnidirectional invisibility, I mean for waves coming from all possible directions. And finally, the cloaking should work also if we try to make invisible several objects, not only one. The state of the art here is very simple, because requirements 1, 2, 3, 7 have been simply ignored so far. Requirement 4, 5, 6 have been only purely satisfied. So I would like to concentrate, instead of speaking of analytical results, I would like to concentrate on the few experiments available in this field. So the first experiment, very clever, has been produced by Wegener and his group, and is sketched here. It is based on a clever idea pointed out by Farah, Gounod, Enoch, and Sasha. It works with 20 concentric rings of 16 different metamaterials. We may see them here. It's very complex. And the cloak works within a range of 200, 400 per. So we see here this proof of cloaking. This is the situation without cloaking, and this is the situation with cloaking. And it's clear that the cloak works because the situation here is much less perturbed than there. So this is one experiment, the first experiment that has been attempted. A few years later, another experiment comes from people, actually some people from my group, Diego Misseroni, Sasha, who was working in Trento at the time, and Jan Jones, Natasha, and Daniel Kochwitz. And again, this is based on a clever idea, and it works with 10 rings of beams following the so-called cloaking transformation rule. It means that we have a plate with a square hole here, and if we look carefully there, we see all these layers of curved beams. So the experiment are here. I don't want to enter into details. They work with sand, and they show that cloaking can be achieved, but it works only at a certain specific frequency. And so our idea was, can we do better than this? And here I would like to show you our result. Don't ask me what is this number. It's a number which, which classifies the effect of cloaking. When this number is 1, it means that the cloaking does not work. When it is higher than 1, it means that the cloaking is worse than nothing. And when it is 0, it means that the cloak is perfect. It works perfectly. And so these spots are the following. I am proposing to obtain the cloaking through reinforcement in stiffness and reinforcement in mass redistribution. So the idea is to keep the stiffness and the mass redistribution separated. To achieve the stiffness, we use a layer of very stiff and light material. And to compensate for the mass, we use a punctual mass redistribution, which does not introduce any further stiffness. This is the trick. So let's look at these spots. When we compensate only for the mass and the inertia of the material and not for the stiffness, we get the blue spots. And we see that in this case, if we only compensate for the mass, well, we get results which are bad. The cloak is worse than nothing. The green spots are better, and is the case where we do compensate only for stiffness, but not for mass and inertia. And so what we see is that things here go better because there are bad points like this, but there are also good points like that. And eventually, I would like to attract your attention on the red spots, because the red spots work pretty well. The red spots refer to the case where we reinforce both for the stiffness and we compensate for the mass. And in this case, we see that the cloaking, there are points where the cloak is almost perfect and is never so bad in a huge range of frequencies running from 0 to 400 Hz. And now I don't want to show you any theory. I would like to show you experiments. And I would like to, first of all, to introduce this experiment. We have a plate here, number one, which is impact. We have the same plate, number 3, where we have cut 3 equally spaced and equal holes. And we have the plate number 2, where the same holes have been reinforced and with their redistributed mass. And the idea of this experiment is to shake the bases of the 3 plates simultaneously, and so to show that plate number 1 and plate number 2 have the same critical resonant frequencies, and the plate number 3 has different resonant frequencies. So when the plates number 1 and 2 will be resonant, the plate number 3 will do nothing, will be undeformed. And vice versa, when the plate number 3 will be under resonance, the other 2 will do nothing, will be almost indeformed. And now let's see the experiment. So we see our comparison between the 3, all shaped the same way. And let's look for the eigenmodes. This is the experimental setup. First resonant mode, we see that these two plates doing the same, the other does nothing because it's not at resonance. Now, this is the unreinforced void is at resonance, the other two do nothing. So they behave the same. Same thing for the second resonant mode. Now is the unreinforced plate under resonance, the other two behave the same. Third resonant mode, same thing, same method. So the reinforced plate and the intact plate, they behave almost the same. Fourth resonant mode, same thing. So up to the fourth resonant mode, the reinforced plate and the intact plate behave exactly the same. Now you might ask me why you didn't try with higher frequencies. Because the experiment becomes difficult, because the deformed shape, the plates deform so small that it's difficult to see them, to detect them. So we were interested to continue with this vibration of the plates, and we did it numerically. And with the first arrangement, we have shown that the resonant modes coincide up to the 15th mode. So they continue to be identical for a broad range of resonant frequencies. But we wanted also to prove that what we found works also when torsional effects are dominant. So we said, why not to put many voids in a disordered way? So we may see here, sorry, I don't see the pointer, yeah. Here, we see here 7 voids randomly disposed and with random inclinations. And again, we would like to compare on the left the impact plate with the reinforced voids and the plates perforated with the void without any reinforcement. We did not do the experiments for this, but we did the numerical simulations. And so I will show you in a second a movie with the numerical simulation where the message is that the reinforced voids behave very well, almost identically to the impact plate. We see here a resonant mode at 90, another resonant mode. We see the two plates behaving the same, and the perforated plate doing almost nothing. So we have here 6 modes where the behavior is almost coincident, and these modes do involve torsion. So these modes are, let's say, an evidence that this kind of reinforcement works pretty well for invisibility. And with this very last movie, I thank you for the attention, and I wish you a nice day.
Thank you very much, Davide, for this wonderful talk. So now the time has come for questions. So